Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of control. As you guys remember, for the previous chapters, we were talking about some kind of the definition of control system, how we can find the relationship between input and output. Where we do have only one input and one output, we use the transfer function because we saw that normal mathematical ways are going to be a little bit confusing, especially when we do have combination of system. And then we found out we cannot only trust one input and one output, which we know it as transfer function. We have to use another way that we know it as a state. So on that point, we were working with matrices. And on that side, we can some kind of understand what is going on for the future, and somehow we can predict the future based on the DNA, based on the matrices that we have inside our system itself. So at this point, we would like to dive down a little bit more inside the transfer function, and we would like to see that what kind of situation would happen to that system and how we can predict the final stage or steady state system, and what are important definitions we have related to that. Without further ado, let's talk about it. As I just talked about that one, when we are talking about a system, we do have some kind of the physical system. It could be a mechanical one, it could be some kind of, for example, the robot antenna, it could be anything. But before doing anything, before some kind of building a system, we have to make sure that everything works well based on the inputs, based on the environmental condition, based on the error, and based on anything that we do have related to that. At the end of the day, we have to make sure our system works. That's why we have to build it, or we have to make a digital twin. Our digital twin is going to resemble or mathematically resemble the whole system itself, and based on that we can understand what's going on. As I just told you, we can predict exactly how a physical system will behave just by looking its math. We don't have to do any kind of expenses, because again, it's hypothetical model related to the actual model itself. It's just about no limitation, and we just about prototyping. As we just talked about it, the very first thing we learned about the control system was about the relationship between input and output. So this relationship can show itself as something we call as a transfer function. So we saw that in the time domain, we had a couple of issues, mathematical issues, and also about something related to the combination of system. That's why we move to the transfer function, which is going to rule in the frequency domain. And this transfer function is going to have two important parts: the numerator and denominator. So denominator is going to be the important part, because this guy is going to give us a valuable information about the whole system itself, and that is the poles. By knowing the poles, by knowing at which side of the S-plane, by the way, you guys remember about the S-plane is a plane that has the real side and imaginary part, and based on that we can understand our poles or zeros are going to exist at what part. So by knowing the poles and by knowing their places, we can understand that how a system would react based on the input itself. For instance, we can understand this speed, we can understand this oscillation, we can understand its stability. The golden rule over here is the poles of your transfer function completely determine how the system will respond. By studying those poles, we can understand what's going on with the system itself. So the very first system that we had was about the first order system. A very bold example of that is about the RC circuit, when we do have the resistance and we do have the capacitor, and we would like to find the voltage of capacitor based on the input voltage. We are going to deal with the system that we know it as the first order system. So first order system is going to just only have one pole. So at this point, pole is going to be -1 over tau. So this exactly one pole is not going to have any imaginary part. As I just mentioned, we are going to work on S-plane all the time. S-plane has the real part on the x-axis, and it has the imaginary part on the y-axis. Important thing that we have to know is that while you look at this pole, you see that it has a relationship between a value which we know it as tau. So tau is going to something we call as a time constant. What is time constant? Time constant in the first order system is the amount of time that it takes for that specific system to reach to its 63% of maximum. So at this point, you can see that for a specific tau, we do have this timing, and the timing is going to show that how fast the system is. Obviously, as you can see, if my tau is going to be smaller, it means that my system is faster. So another important thing that we can understand between the tau and the place of that specific pole is the indirect relationship. It means that if we talk about the distance, for instance, if we do have the distance, and this distance is related to 1 over tau itself, means that wherever your tau is going to be bigger or smaller is going to have indirect impact over your distance. If your tau is small, means that your distance is high. It means that for the further your pole is from your, if it's from your core, was from the 0, 0, means that your system is going to be faster and faster. That's why in the previous videos we talked about it, and I told you that if your pole is way further from your core, it means that your system is going to be faster, and you can completely understand and you can completely see that why that happened. So we do have the 1 tau, and most of the time 5 tau is going to be considered the time that it takes for the system, or for, at this case, for example, for my capacitor to reach to its fully charged. So we talked about the frequency domain, but this, some kind of the time domain formula of our specific system is going to be like this. The yt, which is output, is going to be k times 1 subtracted by e to the power negative t over divided by tau itself. So another important thing is about the anatomy of oscillation. As I just talked about it, when we do have a system, especially when we do have the second order system, means that we do have 2 poles, we are going to deal with oscillation itself. So the oscillation is going to happen because of what? Because of my imaginary part, or because of this some kind of the negative side, this negative or positive side. As you can see over here, I do have my poles as negative delta plus minus j omega. So this omega, or this imaginary part, is going to cause oscillation. On the other hand, we do have my real part. So the real part, as I just mentioned, is going to be, sorry for my kind of misinformation at this point, because this part is going to play your real action, which means that this negative delta 1, and this omega, which is going to act as the sine of omega t in the time domain, is going to act as oscillation, because we know that the sine of omega t is going to be like this, but the trend is some kind of exponential function is going to be like that. It means that it tries to reach to the steady state. So by combination of these two, at the end of the day, we know that for the second order system, we do have the formula like this. It means that I do have my real part and I do have my imaginary part. The combination of this is going to give me something like that, and at the end of the day, I know that my system is stable. So the very first thing that maybe you have in your mind is that, okay, how come you understand your system is stable? Because, for instance, if you're looking this hypothetical condition, we can see that our poles are completely on the left side of my S-plane, and that was a thumb rule. The thumb rule would say that if your poles are going to be on the left side of your S-plane, means that your system is going to be oscillated, or I'm sorry, your system is going to converge and is going to reach to the steady state system. But on the other hand, if I do have my poles on the right side, means that my system is going to be oscillated, or it's going to some kind of have the constant oscillation or increasing oscillation, which is not good and we don't like it, or it says that our system is not stable. So as you just see, it's not just magic. It's just something that based on math and based on the place of your poles, or based on the location of that, you can completely understand what is going on. And 2 important things we understood is about the oscillation, which is going to be your omega, which is going to obviously your imaginary part, and we do have the real part that is going to act as the exponential decay, or it means that that guy tries to reach to the steady state or stable system if we know that everything is going to be on the left side. So another thing that we have to know is about the damping. Obviously, you guys know damping means that how much your system is willing to fight against the changes. It means that any kind of disturbance happens to your system, your system tries to fight against that, try to make it vanish, try to mitigate that. So that is something we call as damping. So damping obviously is just a number. So it's going to start from 0 to 2 or maybe more than that, but we are going to talk about only 5 of them. At the point that when I do have the damping of 0, we can consider the fact that my poles are going to only be imaginary. And as you just know, the imaginary part is related to the oscillation. If you do have only imaginary, means that your system is going to be oscillated. So this is something that we call as undamping, because it oscillates forever. Another thing that we do have is omega of 0.3. Still is not that big, it still is near 0, but it's not that bad. So at this point, I do have some kind of poles, and both of those poles are going to be what? Both of those poles are going to be on the left side, but with this specific condition that I don't have what? I don't have that kind of imaginary part. At this point, I have to consider the imaginary section. But you can see over here that I do have a little bit of oscillation. Again, remember that any oscillation that you see for the system itself is related to imaginary. So if I would like to find an error for my own slide, I can say that this guy shouldn't be like this. This guy, for instance, should be something like that. But since that some kind of poles is on the left side, I know that the system is stable. Since the imaginary part is not that kind of a big deal, means that I don't have that much of oscillation. And since I do have the real part, or the real on the real axis, I know that I'm going to have the stable system. So this one is going to be underdamped. It means that it's a little bit wiggly. On another point, we do have this damping ratio of 0.7, which is the sweet spot. Most of the time, we would like to have something like this. It means that I do have the real part and I do have imaginary part, but both of them are considerable. It's not like the previous one that we had the imaginary part that somehow we got rid of that. That's why my poles were stick to the real axis. At this point, I do have the imaginary part, which is going to be considerable, and these guys are going to be like this. So on that point, you can see that I do have a little bit of oscillation, but my whole system is dominated by what? By my real poles. And real poles means that they're trying to reach to the steady state so fast. So this is the optimal balance between oscillation and reaching to the steady state condition. When we do have some kind of the damping of 1 means that my system is going to be like that. It's going to be some kind of critical damping, and if my some kind of damping is going to be 2, it means that I do have the over damping. Maybe you guys have a question at this point, says that, okay, you told us that our system is not going to be stable unless that our our poles are going to be on the left side. But at this point, we can vividly see that I do have 2 poles on the right side, and at this point, I do have 1 pole on the right side. So at this case, I can say that since you don't have any imaginary part, you're not going to deal with any oscillation. So mostly your system is going to be act as an exponential function. It means that those guys would try to reach to the steady state system. However, if you do have your poles on the right side, it doesn't necessarily mean that your steady state is something that you like. It is going to act based on its instincts, based on the place of the poles. Still, it's not that bad, but also it's not that good. That's why I would like to emphasize that every time that you build a system, or at least try to design a system, you have to make sure that all of the poles are going to be on the left side, despite of the fact that they do have imaginary or some kind of the imaginary or real, or both of them at the same time. So the damping ratio is some kind of the zeta. It's going to act as the system character dial, and the zeta of 0.7 is the definition of engineering sweet spot for speed without excessive overshoot. So we would like to make our system to act something like that. Another important thing that we have to know is the natural frequency. Obviously, you guys know the natural frequency means that how much is the specific frequency related to our system if we don't have some kind of friction, or if we don't have any disturbance from the outside. But important thing about this omega n is that we have to find its relationship between the poles and omega n itself. Imagine that you do have 3 conditions. I do have 2 poles like this, another 2 poles like this, and another 2 poles like this. Omega n is going to follow a specific formula, and this formula says that it's going to be the delta to the power 2 plus omega d to the power 2 and the root of that number. So at this point, you do have your real part and you do have the omega d, which is going to be your damping frequency. So by considering these two, or by having a very, very intuitive definition of the omega n is going to be fine based on the distance of your poles with the core itself. It means that if you do have the more distance from the core, means that your omega n is going to be higher and higher. By knowing that your omega n is going to be higher and higher means that your frequency is higher, or it means that your system is going to be faster. So at this point, when I do have 3 different conditions, that when the distance is going to be like this, is going to be like that, and it's going to be like that, again based on the some kind of the location of the real number, you can see that my system at the first point, if I assume that my omega n is 1, the system is going to be like this. Is stable, but still is going to be slow. Then I do have the omega n as 5. It means that my system is going to be faster, and then I do have the omega n of 10, which is going to be, the system is going to be the fastest. And it completely makes sense, right? Because if you guys remember, for the previous part, I told you if we do have The first order system, by the way, right now we're talking about the second order system because we have two poles. If you do have the first order system, your timing or your tau has the indirect relationship with the frequency or the speed itself. It means that if my timing is going to be less, my frequency is going to be higher. Another thing that we know, it has the indirect relationship with distance itself. It means that whether my poles is going to be further from the core itself means that my system is going to be faster. And we also can see over here. But at this point, since we do have two poles, means that for finding the distance, we have to follow this formula itself. But at the end of the day, the concept is the same. So a very quick approximation is that about the response time is going to be 4 divided by zeta times omega n itself. And doubling the distance, obviously from the origin itself, is going to cut the response time in half. So this is very intuitive. It's not very based on the example, based on the numbering and based on the calculation, but I would like to give you a big picture that what is happening if you do have the poles, that its distance is going to be further in comparison to another one. So another important thing that we have to know is about the zeros, because obviously, as I just told you, poles are going to play a very crucial role. But what about zeros? Because obviously they're part of the system itself. It doesn't necessarily mean that those guys are going to sit beside and do nothing. So at this point, I do have two systems. The very first system, as you can see, it's a second order system. I do have two poles. And if I imagine that my zeta is going to be 0.7, it's sweet spot. I do have a little bit of oscillation, or I do have a little bit of overshoot. Then I do have the steady state system. But another point, I do have another system. It's going to be the same poles, but at this point I do have this some kind of the zero, and this zero is going to have a little bit effect, and it means that by having the zero itself is going to be snappy rise, and I do have the higher overshoot. So what does it mean? It means that zeros do not determine the stability, because the stability is something related to the poles. If I do have my poles on the left side of the S-plane, means that everything is fine. But on the other hand, zeros are going to modify how system gets to its final state. So another important thing, or the thumb rule, is that the zero near pole will partially cancel the pole's effect itself. So this is very important part. So again, right now everything is intuitive. We are not talking about the numbers. For the next part, we are going to definitely touch some examples to see that what's going on. But at this point, we understand that by having the zero in our system itself, somehow we can control the effect, or we can control something we call as the transient response of the system. I do have, by the way, I believe I talked about it in the previous videos, but we do have two important parts. The very first part is about the steady state system, which is going to tell us that it's if whether the system is stable or not. And another part is about the transient section. So the transient section means that something that happens at very fast, and I would like to see that what would happen to my system. Based on the zeros, I can see that what's going on. Obviously, poles have a little bit of effect over that part, but the poles effect mostly is on the steady state parts. On the other hand, zeros are going to show themselves on what? On the transient part. So as you can see, think of the poles as an architectural foundation and zeros as the interior styling. And we can some kind of get the structure right first. As I just told you, we do have the absolute law of stability. The absolute law of stability, which says that if you do have your some kind of S-plane system, that it has the real part and it has the imaginary part, the thumb rule, or this absolute law, which says that if your poles are going to be on the left side of the system, it is something sweet spot. This is something good that we like, means that our system is stable. On the other hand, if you do have your poles on the right side, means that something is wrong. By something is wrong means that either my system is going to be oscillated like this, is going to be the constant oscillation, or something we call as marginally stable, or is going to be completely unstable response. It means that when you have some disturbances, or when you have a small oscillation, this oscillation is going to be amplified. So you can see that in lots of examples. For instance, when we're talking about it in electrical circuit, if I do have the harmonics, or if I do have some disturbances for my frequencies, and if my system is not good enough, it doesn't have enough good damping, and it doesn't have enough good poles, means that those kind of disturbances are going to be amplified. And amplification means that your noise are going to get bigger and bigger, and your system is going to be completely unstable. Obviously, this is something that we don't like. So in a linear system, we can call that system, we can call that stable if and only if all the poles are going to be the left half plane. Even one single pole and the red zone makes the entire system totally unstable. So this is non-negotiable. By the way, as I just told you, right now we are talking about the real and imaginary. But in the case when we do have the real ones, the system is going to be somehow stable, but it doesn't necessarily mean that this steady state is going to be something that we like. And at some point, if we are not going to have a good system, that steady state is going to be catastrophic. It's going to cause us so much problem. So try to keep your system on the safe spot. Another thing that we have to know is about the domination of poles, because as I just talked about it, we do have the distance between the poles and the cores itself. And I told you about it that if the poles are going to have higher distance with the core itself, their effect is going to be fast. Imagine that I do have some kind of the fourth order system, means that I do have 4 poles. I do have 2 poles that are going to be like this, and I do have another 2 poles like that one. So you can see the very clear difference between the poles itself. While I do have these 2 poles, I know that these 2 guys are going to act fast. On another hand, I do have these 2 poles that I know these guys are going to be stable, but are not that going to be that fast. So at this point, I'm going to show you the difference between the first one when I do have the 4 poles and the second one when I do have only 2 poles. Imagine the curve 1, which is going to be red one, has full 4th order exact response. On the other hand, I do have this dotted one, which is going to be 2nd order. It means that at this point, I don't have that 2 poles. As you can see, so when we do have some kind of the curve 1, which is going to be the 4th order, some kind of exact response, and the curve 2 is going to be 2nd order dominant approximation, we can see highly those 2 curves are going to be identical. But why they're identical? Because as you can see over here, the poles on the left side, or like something that we call it as the fast response poles, are way have more distance in comparison to the normal poles that we do have what we call as dominant part. So at this point, we can say somehow their impact on the system itself is going to be fast, and also is going to vanish so fast. That's why at some points, if we see that our poles are going to be, their distance of our poles are going to be way higher than the normal or some kind of the dominant poles, we can somehow get rid of them. And we can say that, okay, at the very beginning of the point, they do have a little bit of effect, but their effect is not that much. So somehow we can get rid of them. So by getting rid of them, our 4th order system just became the 2nd order. It means that the impact of those 2 poles, which are just vanished, are not going to be highly on the whole system itself. And our 4th order system just became the 2nd order system. So what we understand over here, that it means that you don't need to overcomplicate things. So professional engineers design based on the dominant slow poles, the very variable system itself. What does it say over here? It means that engineering loves or some kind of tries to simplify everything. And at this point, when you do have the 4-pole system, means that your system is complicated. But when you see that the distance of those 2 poles are going to be way higher than the normal ones, you see that, okay, those poles are there, but their impact is not going to be that much. So somehow I can get rid of that. That's why our 1st order system just becomes the 2nd order system. Another important thing that we have to know about our system itself is about some definitions. So we thought that we saw these definitions. On the next slide, I'm going to talk about the very important formula. But this 4th important definition is related to the peak time, means that how much does it take for my system to reach to its peak from the 0 itself. Then we do have the rise time, means that how much time does it take for my system reach from the 10% to 90%. We do have the peak overshoot, that most of the time we show it with percentage, means that what is the difference, or what is the percentage of difference between the peak side and the steady side of my system itself, which is something that I would like to reach. And finally, we do have the settling time, means that how much does it take for my system from the beginning to the end in order to reach to the steady state part. What is the steady state? Means that the error or the difference between the final value that I would like and the actual value is going to be less than 2%, or something we call it as error. So by knowing these 4 important definitions, we can somehow decide about how fast the system is, how smooth the system is, and all other kind of information related to that. So these 4 formulas are very important, and I highly recommend you guys to understand them, or at some point try to memorize them. Obviously, if you don't memorize them, you can all the time bring your cheat sheets, but these 4 formulas are important. The very first one is about the settling time, means that how much time does it take for my system to reach to that what, as you can see over here, to reach to that steady state part. And it's going to be 4 divided by damping, or the zeta, times omega n. If you guys remember, if our omega n is going to be small, means that the TS is going to be high. Means that if omega n is small, it will take more time for my system to reach to what? To reach the steady state system. Imagine that I do have the condition that my zeta is going to be 0.7, which is damping, sweet spot. My omega n is going to be 5, and my TS is going to be 1.14 second. Another important formula is about the peak overshoot. Means that how much is the difference between my peak value of the some kind of actual value of the system and the final value, the final value of that one, or the steady state value of that one. If we show this OS bar percentage itself is going to be e to the power negative zeta times pi divided by square root of 1 subtracted by zeta to the power 2 times 100%. So these numbers are going to be a little bit intuitive. The number that most of the time we use, again, this is going to be sweet spot. Imagine that I do have the case that my zeta is going to be 0.5, because as you can see, this is the function, that its only input is the zeta itself, and it is completely related to that. And the zeta, if is going to be considered as 0.5, my overshoot is going to be something around 16.3%. Another important part is about the rise time. The rise time means that how much does it take for my system to reach from 10% to 90% of its value, and it's completely and highly related to omega n. Means that if my omega n is going to be small, my TR is going to be high. And imagine that in a condition that when you have omega n as 5, my TR is going to be 0.36 second. So you can see that this natural frequency is a very important value in the whole, some kind of in our world itself. Another part is about the peak time itself, means that how much does it take for my system to reach from 0 to the maximum overshoot, which is something that we call as TP. And at this point that we do have the zeta of 0.7, the omega n is 5, my TP is going to be something like this. And another important thing, and one final slide of this part, is going to be the vector map of the system behavior itself. Because as you guys remember, when we were talking about the poles itself, the very important part, or the first important thing, is about its distance with the core itself, which we call it as omega n. This omega n is going to tell us that how fast the system is. As you guys know, the further this omega n is going to be, the faster the system is. So by finding the distance based on the formula that we had, based on the formula that I showed you, we can understand how fast our system is. But another thing that we have to focus on is about the real side and the imaginary part. And the real side is going to be what? So we do have the real part and we do have imaginary part. So the real part, as you guys know, is going to be related to our exponential system, or the decay, or how some kind of the convergence my system is going to be. And on the other hand, I do have the imaginary part, is going to say that how much oscillation I'm going to have. This imaginary part is going to be follow this formula, the omega n times root of 1 subtracted by zeta to the power 2, which is something that we call as the oscillation frequency. And then we do have another part is going to be the real axis, is going to be controls the decay itself, and it's based on the some kind of the speed that we call as the TS, while the imaginary part is going to be the TP itself. Another important thing is about the angle. The angle of this one, or the theta itself, is going to show us what's the damping ratio. So this one means that the smaller angle is going to be, we are going to have the higher damping ratio, and it means that we do have the less oscillation, if you guys remember from the previous slides itself. So at this point, we are going to answer 3 important questions. The very first one is that, is the system stable? So as you guys know, if I do have my S, or if I do have my poles on the left side of the S planes, everything is fine, means that my system is stable. Is the system is going to be fast based on the distance that we found, based on the formula that we know for our omega n itself, which is going to be root of delta to the power 2 plus omega d to the power 2. We are going to have what? We are going to have this omega n, which is the distance. And the higher this distance is, means that my system is going to be faster. And finally, will it's going to be oscillate. The oscillation is completely related to my imaginary part. By studying that part, I can understand my system is going to be oscillated or not. So the final slide is just related to the recap of this part of this some kind of chapter. So as we just saw, the theoretical laws which says that all poles must be on the left side if I would like to have the stable system. Complex poles is going to be mandates the physical oscillation, and dominant poles means that the ones that are going to be closest to the origin is going to dictate the behavior or steady state condition, while those ones that are going to be further from our origin itself, those guys are going to have a little bit of impact, but since those impacts are going to be fast, it means that there are going to be very, very slight impact on the whole system. And finally, zeros are going to modify the transient shape, not the stability itself. On the other hand, we do have the practical engineering power. Imagine that you have the damping ratio of 0.7, which we know that sweet spot is going to provide the optimal response balance, and the distance from the origin or omega n is going to scale the system speed. The further my omega n, or the higher my omega n is, that the faster there's some kind of this means that the faster my system is going to be. And the four metrics that we call as the race time and the peak time and about the overshoots, and we do have the stable time, the steady state time, is going to define the feel of the system itself. And finally, the vector map that we saw at the final side is going to be going to show the performance prediction without some kind of the simulation itself. So as we saw over here, we just talked about a very important definition or very important chapter related to the control system. We talked about the poles, we talked about some kind of zeros, we saw that what would happen if I do have the further distance from some kind of the core itself, and what would happen to the zeros, what would happen to the poles. We talked about the dominant poles, we talked about the transient, we talked about the steady state part, and at the end of the day, we decided that if I would like to have the very, very big picture, some kind of decision related to my system, I can just study that by looking at that real part and imaginary part, and by looking at those oscillations itself. By just studying those, I can understand at the end of the day, or I can predict that how my system is going to react based on the specific input or based on the disturbance itself. So for the further chapters, we are going to talk about them in detail. We are going to have some examples to completely understand it. If you have any questions related to this chapter, I would be more than happy to answer that. Don't forget to follow, share, and comment, because it's going to be very helpful for me. My name is Mahmoud Kiasari. Have a super great day, night, whatever. See you around.